Okay, so today we're going to start on the Poisson distribution. So it is a French word, that's the pronunciation, the Poisson distribution. I'm going to start by thinking back to the binomial distribution. The binomial distribution had two parameters, n and p. And what we were looking for with the binomial distribution, what we were measuring, the actual discrete random variable, was the number of successes out of a specific number of trials. So out of n trials. And we also knew the probability of success of each particular trial. So it was the number of successes and we knew n and p. The possible outcomes for the number of successes, so the sample space, went all the way from 0 successes as the minimum through consecutive integers until you got to n successes as the maximum. So the number of trials. If you had 10 attempts, you can't have more than 10 successes. So that's what I have on the screen. The distribution name and parameters, a description, and the potential outcomes. Only some situations will fit the binomial distribution. We knew the criteria to model with the binomial distribution was that we needed a fixed number of trials, a constant probability, only two possible outcomes, and for each trial to be independent from all other trials. If all of this criteria was met, we could model with the binomial distribution. Well, other situations can be modeled with other distributions, and today we'll start with the Poisson distribution. The Poisson distribution has only one parameter, that's lambda. Lambda is going to represent the average rate which something happens. A description of what we're measuring with this discrete random variable is how many events occur within a particular period of time, given that we know the average rate at which they normally occur. And when we look at the outcomes can be any integer in between 0 of this event occurring in that period of time through all of the consecutive integers until, well, here you can see there is no maximum point. Technically, this is an infinite distribution. There is no cutoff, there is no maximum. There wasn't a fixed number of trials, so there isn't a ceiling value to have. The probability of having lots and lots of occurrences, the probability of having 100 successes, is going to be extremely low, but it does, however, exist. Okay, we'll talk more about the situations that can be modelled as Poisson, but first let's look at the need for the Poisson in the first place. So, let's consider this situation. We've been asked to calculate the probability of 8 cars passing the school in the next hour, given that we know on average 5 pass every hour. Well, if we wanted to use the binomial distribution, what could we do? We could take the 1 hour and we can split it up into 10 slots. So each of these slots is 6 minutes. And we can say if a car comes past in this 6-minute slot, we'll say that's a success. And if no car comes past in the 6-minute slot, we'll say it's a failure. So 10 available slots. If we expect 5 cars on average, that should mean that the probability of a car coming by in any of these slots is 5 out of 10, 1/2. So that would lead to a distribution x follows a binomial of 10 and 0.5. We can do our normal calculation, 10c8, 0.5 to the power of 8 for the successes, and 0.5 to the power of 2 for the failures. Obviously, you can use the BCD mode on your calculator, and we get this answer. So that was us using the binomial distribution to get here, but there is an issue with the way that we've done this. We've just said if a car comes by in that 6-minute slot. Well, 6 minutes is quite a long time. What if I got 2 cars? There'll be no difference from if I got 1 car. What if 10 cars came by in that 6-minute slot? Do I just tick it once? I can't have 10 ticks. It's either a success or a failure. It was either there was a car or there was no car. There's no scope for multiple cars. So technically, it's not actually the count of how many cars came by. It's just whether or not there was traffic on the road in each of those intervals. We can try to fix that. We can make the time slots smaller. So instead of 6-minute intervals, let's make them 3-minute intervals. And we can do a similar process. 3-minute intervals means there's 20 intervals. The probability we calculate now is going to be 1/4. We can once again do our binomial calculation, and now we get a different answer. Now we get 0.0609. It's more likely to happen. Why stop there? We can still get multiple cars in a 3-minute slot. Why don't we make the slots 1 minute? So then we'd have 61-minute slots. Why don't we make the slots 10 seconds wide? Why don't we make the slots 1 second wide? We can make the intervals infinitely smaller, meaning there are more intervals, and we'll probably get a more accurate answer. But I'm sure you know that within an hour, there are 3,600 seconds. So the binomial is going to get quite unwieldy if we kept on taking this approach. Instead, we can use some maths which you're going to eventually get to, which is using the limit of this expression. So as n, which is the number of intervals, increases, and as it approaches infinity, so an infinite amount of intervals, the expression, the probability function that we have for the binomial starts to turn into something very different. It starts to turn into this exponential expression that we have here. E to the negative lambda multiplied by lambda to the x all over x factorial. This is the Poisson distribution probability function. You don't need to understand all of this, but I do just want you to realize we don't just pluck things out of thin air. There is some connection and some reason to how these probability functions have arisen. So, if we needed infinite time slots, we will generate a Poisson probability function. This you can now write down, the definition of the Poisson distribution and its probability function. The probability that a random variable x equals an outcome x can be found using this calculation, e to the negative lambda multiplied by lambda to the power of x, all divided by x factorial. Okay, let's actually try this out. So, in this first one, we've been given the distribution. X follows a Poisson distribution where the lambda value, where the average rate of an event occurring is 1.2. We've been asked to find the probability that that event happens 3 times. We're going to use the probability function. We're going to substitute 1.2 for lambda, and we're going to substitute 3 for x. So that gives us e to the negative 1.2. Then we have 1.2 to the power of 3, and we're dividing by 3 factorial. We can just type this into our calculators, and we get 0.0867. Remember that the factorial button, you'll need to go to options, scroll to the right, and there'll be a probability menu, and in there you'll see the factorial button. Okay, that's the probability that it equals exactly 3. How about the probability that it's greater than or equal to 1? Well, that is going to be the probability that x equals 1, plus the probability x equals 2, plus the probability of 3, plus the probability of 4, and we just need to keep on going up until we get to the maximum number. But obviously, with the Poisson, there is no maximum number. So this is going to be futile. Instead of going in that direction, we can say this is going to be 1 minus everything below 1. The only thing below 1 is actually 0. So 1 minus the probability x equals 0. And that is going to give us 1 minus e to the negative 1.2 multiplied by 1.2 to the 0 all over 0 factorial. Before we even go any further, I want you to check 2 things for me. Firstly, I think you should know this one. What is 1.2 to the power of 0? Check on your calculator. Secondly, what is 0 factorial? If you've checked both of those things, I'm sure you can see a much easier way to simplify this expression, to simplify this fraction. So you knowing what's happening with both of those two terms helps you to write this out. I'm not going to tell you. Check on your calculator. From there, we can calculate this to be 0.6988. Part C, we have an inequality. X is in between 3 and 5. It includes the 5. It doesn't include the 3. You know that we like to write these expressions with the outcomes that are included. Those are the ones we'll use in our calculators. So rewriting this as x is in between 4 and 5. That's the probability x equals 4 plus the probability x equals 5. Substituting the correct values into the probability function, we get the calculations that we're going to type into the calculator. And this can go into the calculator all at once, 0.0323. So this is the probability function. You're going to need to be familiar with this for lots of the problem solving that we're going to encounter. There is a function on your calculator which we'll come around to later on, but it doesn't mean we're going to neglect learning and utilizing the probability function. Okay, here I've got a quick question in context. Given that a website receives 25 hits a second on average, very popular website, determine the probability it receives 20 hits in the next second. So firstly, just going to define the distribution. X follows a Poisson distribution with 25. There were 25 hits each second on average. Well, in this particular second, what's the probability of 20 hits? So we're looking for the probability that x equals 20. We have our value for lambda and we have our value for x. Just substituting them into the probability function will once again give us our answer. So 0.0519. Now the first section of the first exercise I give you, I'm going to want you to use that probability function all of the way through. But there are two other ways in which you can calculate Poisson probabilities. There are some tables that have been made and produced that can help you define Poisson probabilities. These are in the formula booklet. These will be available in the exam. It is useful to know how to use them. And then obviously we have a function on our calculator which helps us out as well. Let's get to how we do this on the calculator. Just like the binomial, we're going to go to the options menu, stats menu, distribution, and you're just going to look for Poisson. When you choose Poisson, we're going to be making use of the PCD, the Poisson cumulative distribution function. And the syntax, I've put that here for you. We put in the minimum value we're interested in, the maximum value we're interested in, and then the lambda parameter. Okay, let's try that out. Here in this question, we've been told that on average, 8 cars come down a country road each hour. We need to find the probability that less than 5 cars pass in the next hour. Well, firstly, let's write the maths for this. The distribution is going to be defined as x follows a Poisson distribution where lambda equals 8. Part A, we're finding the probability that x is less than 5. It doesn't include 5. We're going to rewrite this with a number that's included. So we're going to rewrite this as the probability x is less than or equal to 4. Okay, let's use the calculator function and get the syntax correct. The minimum value I'm interested in is 0. The maximum I'm interested in is 4. We're going to use PCD 0, 4, and then we put in the parameter 8. Enter on the calculator, and we get our answer, 0.0996. Well, we could have also got that from the tables. How you use the tables, we first look for the parameter in the top row, and we're looking for 8, and we know that that's the column that we're using. And then we need to look for the number that we used in the less than or equal to statement. So we're looking for 8 and we're looking for 4. So 8 lets me know I'm using this column, 4 lets me know I'm using this row. The number that's both in the column and the row, 0.0996. So the calculator and the tables are giving us the same values. Let's look at part B. At least 3 cars pass. At least 3 is going to include 3. It's going to be greater than or equal to 3. 3 should be the lowest. 3 should be the least. Considering though that there is no top value, I wouldn't be able to put in a maximum value for the Poisson. We need to use a 1 minus. So the probability x is greater than or equal to 3 equals 1 minus the probability x is less than or equal to 2. That's 1 minus PCD, the minimum of 0, maximum of 2, parameter of 8. On your calculator, you can find the PCD, and we're going to do the 1 minus to get our answer of 0.9862. Where could we have used the tables to do this same question? The tables are only set up to find less than or equals to probability statements, so I can't use it for greater than or equal to 3. I could have used it for the less than or equal to 2. I could have used it to find 0.0138. Let's have a look. We know we're working with the parameter 8 or 8.0, and we wanted less than or equal to 2. So we'll just go to the row for 2, read across the number that's in both of them, 0.0138. And then we could have done 1 minus to get our final answer here. Okay, and then moving on to part C. The probability that the number of cars passing is between 2 and 5. The inclusive here lets you know both of those numbers are involved. So I'd always just write the 2 and the 5 and then just double check. Is the 2 included? Yes. Is the 5 included? Yes. Your minimum is 2, maximum is 5, parameter is 8. 0.1882. It's a little trickier to use the tables to get this. We would have had to look up the probability x is less than or equal to 5. And then we need to get rid of some of those values. I don't want everything below 5. I don't want to include 1 and I don't want to include 0. So I'd have to subtract the probability of less than or equal to 1. That would have got us 0.1912, subtract 0.0030, and I think you can see that that gets us our same answer of 0.1882. That's a little bit of a trickier way to use the tables, why it's such a benefit that we have such powerful calculators that will help us out in this situation. So, this is how we would use our calculator or the tables to work out Poisson probabilities. The benefit of the calculator over the table is that the table is only designed for certain outcomes of lambda, for increments and multiples of 0.5, from 0.5 all the way through to 10. So if I had a lambda of 7.1, the tables wouldn't help me. And finally, we just want to look at how we might be able to work backwards and do a little bit of problem solving. Let's see how the tables are useful here. We know that we're working with lambda equals 7.5. If we're told that the probability x is less than or equal to a is equal to 0.2414, well, let's just look down the row 7.5. And if we look down, we're waiting to see 0.2414. Well, there it is. And that matches up with 5. So we know the probability x is less than or equal to 5 equals this probability, a must equal 5. Okay, part B. The probability x is less than b. We know that the tables are set up for less than or equals to. So we're not interested in this probability statement. We need to rewrite it. X is less than or equal to b minus 1. Whenever we change a less than to a less than or equals to, we go for the number underneath. 10 would become 9, 7 will become 6, b becomes b minus 1. Okay, we're going to do a similar thing. If that equals 0.5246, we just need to look down the column until we get 0.5246. Here it is. That lines up with 7. So we know the probability x is less than or equal to 7 equals 0.5246. This means b minus 1 must equal 7 and b equals 8. And finally, part C. The probability that x is greater than or equal to c. Once again, the tables are set up for less than or equals to. So let's rewrite this. 1 minus the probability x is less than or equal to c minus 1. We're going to rearrange this to make the probability statement the subject. So we know that this probability statement equals 0.6620. We're going to look this up. Down the column, we get 0.6620, and it matches up with 8. So c minus 1 must equal 8, meaning c equals 9. Okay, this is your introduction to the Poisson distribution. We've looked at how it arises. We've found the probability using the probability function. We've also found it with the calculator, and we've found it using the tables. We've used the tables to find backwards probabilities, or to use probabilities to find other unknowns, and that will do for the introduction. Next, we'll look at how to model correctly with the Poisson distribution, including when you need to make modifications. And once we've got that, we'll look at some more advanced things like switching between the Poisson and the binomial when that's appropriate. We'll do some more problem solving, and we'll move on to hypothesis testing.